Hello students, I am Professor Dheeraj Kumar Singh from Department of Mechanical Engineering, Sagar Group of Institutions, Sestekar, Bhopal. Dear students, today we are going to discuss available energy and unavailable energy, irreversibility and combined effect of first and second law of thermodynamics. So before starting available energy and unavailable energy, we will discuss the temperature entropy plot, and by the help of that plot we will be able to find out reversible isothermal heat transfer, which will be useful in finding out the efficiency of Carnot cycle. So let's start the class. So dear students, here we can see temperature entropy plot. So in this diagram we can see this is our temperature, this is our entropy, and this is a reversible process starting from I and finishing at F, right? So the infinitesimal change, infinitesimal means very small. So the infinitesimal change in entropy ds due to reversible heat transfer del Q at temperature T is ds equal to del Q by T. So this expression ds equal to del Q reversible by T we have got from second law of thermodynamics by the help of entropy. So we know the formula of entropy ds equal to del Q by T. If del Q reversible is 0, that means the process is reversible and adiabatic. So when a process is reversible and adiabatic, then we know our change in entropy is 0, then entropy will become constant. So a reversible adiabatic process is therefore an isentropic process. Now del Q reversible is equal to TdS, and when we will integrate that del Q reversible, then we will get Q reversible equal to integral lower limit I upper limit F TdS. Dear students, so the system is taken from I to F reversibly in the given figure. In this figure we are talking about this figure, that this process is going reversibly from I to F. Right, the area under the curve integral TdS is equal to the heat transfer in the process. So now we can see for reversible isothermal heat transfer, temperature is constant because it is isothermal process, so temperature is constant. So here we can see this is a curve, and we can say it, this is a process, and this process is a reversible process starting from I and finishing at F. So we have taken a strip here, a point on this curve, and we have projected that point on this entropy curve. And when we will multiply the temperature and the difference of entropy, we will get reversible heat transfer. Right? So area under the curve when projected on entropy axis will give you reversible heat transfer. So Q reversible equal to integral TdS. Here we can see this process is a isothermal process because temperature is constant throughout the process. So what will be the heat transfer in isothermal process, and why we are interested in finding out the heat transfer in isothermal process? Because in Carnot cycle heat supplied isothermally and heat rejected isothermally. So that's why we want to find out the heat transfer in an isothermal process. So here in this process heat transfer will be like Q reversible equal to T integral ds. We have taken T out of the integration sign because T is constant. So after integrating this ds, this will become T into S final minus S initial. So this T multiplied with S final minus S initial will give us the reversible heat transfer. So where SF is our final entropy and SI is our initial entropy. And for a reversible adiabatic process we all know ds equal to 0, so entropy will be constant. Now dear students, move to the representation of Carnot cycle on TS diagram. So this is PV diagram and this is TS diagram. We have already discussed about PV diagram of Carnot cycle, but we had not discussed about the TS diagram. So today we will also discuss about TS diagram. So this y axis is our pressure and this x axis is our volume here. So process 1 to 2 is reversible isothermal heat addition process. This process is isothermal process 1 to 2. That means process 1 to 2 is isothermal, means temperature will constant. So similarly we can plot this process 1 to 2 here like this. Temperature constant 1 to 2. This is isothermal heat addition process. So this line we can see, this 1 to 2 line is constant. That means temperature is constant here, and we have denoted this process 1 to 2 as T1 temperature and this process 3 to 4 as T2 temperature. So we can see that heat is getting supplied in process 1 to 2. So we have already discussed in entropy class that when heat is supplied reversibly in any process, then its entropy will increase. So obviously that arrow will go from 1 to 2 and this will go away from the temperature line, or we can see here that entropy is increasing. So when we will add heat reversibly in any process, then entropy will increase. Now here we can see the process 2 to 3 is reversible adiabatic expansion process, right? Reversible adiabatic expansion process. So we also know reversible adiabatic process is an isentropic process. That means entropy is constant. So here we can draw 2 to 3 as isentropic process on this entropy scale, right? So this on this entropy axis. So we can see S2 is equal to S3, right? So this is expansion work. Then again we can see process 3 to 4. Process 3 to 4 is our reversible isothermal heat rejection process. So this is 3 to 4 is reversible isothermal heat rejection process. Q2 heat is rejecting from here. So we had discussed in entropy class that if we will reject heat from any process reversibly, then entropy of the system will decrease. So here we can see that entropy is decreasing. So process 3 to 4 is reversible isothermal heat rejection process. And the last process which completes the cycle is process 4 to 1, that is reversible adiabatic compression process, right? So reversible adiabatic compression process is also an isentropic process. So 4 to 1 is our reversible adiabatic expansion compression or isentropic process. So now we want to find out the efficiency of Carnot cycle, right? Here the processes and what kind of process will take place I have written here, so you can refer it from here. So efficiency of Carnot cycle can be given as W net divided by heat supplied. So W net will be equal to Q1 minus Q2. We have seen it earlier. This is Q1 minus Q2 is our output and Q1 is our input. So we can write Q1 as T1 into S2 minus S1. We have seen here that if you want to find out Q reversible for this process, then we will be writing T into SF minus SI. So similarly for Q1 we can write T1 into S2 minus S1, right? And for Q2 we can write T2 into S3 minus S4. So we have written at the place of Q1 T1 into S2 minus S1 minus at the place of Q2 T2 into S3 minus S4 divided by T1 into S2 minus S1. After some calculations we will also be seeing that S3 minus S4 is becoming equal to S2 minus S1. From here also we can see that entropy of 2 is equal to entropy of 3, entropy of 1 is equal to entropy of 4. That means difference of 2 and 1, S2 minus S1 will be equal to difference of S3 minus S4. So this can also get cancelled out. So finally we will have the expression T1 minus T2 divided by T1, and the expression will become 1 minus T2 by T1. So this is the expression for Carnot cycle efficiency, 1 minus T2 by T1. T2 is our lower temperature and T1 is our higher temperature, right? So if we want to find out maximum work, so maximum work is the difference of heat supplied and heat rejected. So Q1 minus Q2 is our maximum work. So we can write in this last expression W max Q1 minus Q2 equal to T1 minus T2 into S2 minus S1. S2 minus S1 we have taken common as S3 minus S4 and S2 minus S1 is equal. So this is the expression of our Carnot cycle efficiency, 1 minus T2 by T1. Now move to the results of first and second law of thermodynamics when we combine these two laws together. So dear students, we can see here by the first law of thermodynamics, for a closed non-flow system we are having an expression del Q equal to du plus P dV, and this is our equation number 1. By second law we are having expression del Q reversible equal to TdS. This is our equation number 2. So from 1 and 2 we have TdS equal to du plus P dV. As del Q reversible is same for both equations, so we can write TdS equal to du plus P dV. So this equation holds good for a closed system when only PdV work is present. So this is true for reversible cycle and quasi-static process, right? So dear students, we have got our expression by the help of first and second law of thermodynamics. Now second expression we will get the value of enthalpy H equal to U plus PV. The value of enthalpy H equal to U plus PV. H is in enthalpy, U is internal energy, and PV is pressure into volume. So here we know that this is a small h, that means this is specific enthalpy, right? So when we will differentiate it, we will get dH equal to du plus, when we will differentiate PV, then this will become PdV plus VdP, PdV plus VdP. And when we will take this du plus PdV expression together, then this will become TdS by the help of this equation, TdS equal to du plus PdV. So this du plus PdV will become TdS. So now dH equal to TdS plus VdP, and finally we will write for TdS dH minus VdP. So this equation also relates only properties of a closed system. There is no path function term in the equation. Hence the equation holds good for any process. So finally we are having two equations, TdS equal to du plus PdV, and here TdS equal to dH minus VdP. So these two equations are the final outcome of first and second law of thermodynamics when we will combine them together. Now dear students, we want to find out the entropy change for an ideal gas. We all know ideal gas equation, PV equal to mRT. So we want the entropy change values for ideal gas. As we know, TdS equal to du plus PdV. Earlier I have derived it by the help of first and second law of thermodynamics, that TdS equal to du plus PdV. When we will divide the whole term by T, so ds equal to du by T plus P by T dV. This will be our equation number 1. For ideal gas, we all know du equal to mCV dt and PV equal to mRT. So here we have assumed the derivation for unit mass. So m equal to 1. So du equal to Cv, Pv equal to mRT, and we can write Pv equal to mRT as P by T equal to mR by V. We have took that V into the right hand side denominator. So this will be our equation 1. So we will put the value of P by T equal to mR by V in equation number 1. Then what we will get, integral S1 to S2 ds equal to, at the place of du we have written Cv dt by T, plus at the place of P by T we have written mR by V, right? So here the lower limit will be T1 and upper limit will be T2, and here the lower limit will be V1 and upper limit will be V2. So when we will integrate it, we will get S2 minus S1 equal to Cv ln T2 by T1 plus R ln V2 by V1. R is our characteristic gas equation, P is pressure, T is temperature, V is volume, M is mass of the gas. So now we are having the entropy change, and that entropy change S2 minus S1 is Cv ln T2 by T1 plus R ln V2 by V1. Similarly, we will be able to find out two more expressions, and those expressions are S2 minus S1 equal to Cp ln T2 by T1 minus R ln P2 by P1, and the last expression is S2 minus S1 equal to Cp ln V2 by V1 plus Cv ln P2 by P1. So these three expressions are very important expressions for entropy change for an ideal gas. Now we will move to available energy. What is available energy? It is the maximum work that can be obtained in a cycle, right? So we have taken an example of heat engine, that this is T1 is the source temperature and this T2 is the sink temperature. This is our heat engine which is getting heat Q1 and rejecting heat Q2, and by getting heat Q1 it is producing W max and by rejecting heat Q2, and that W max, that maximum work output is our available energy, right? And this Q2 heat rejected is our unavailable energy. So efficiency is given W by Q1, W is work output and Q1 is heat supplied. So here work output is W max. So maximum efficiency is W max divided by Q1, that will be question number 1. And we have just derived the efficiency for Carnot cycle, right? That maximum efficiency will be, the formula of maximum efficiency will be equal to 1 minus T2 by T1, and that will be question number 2. So by the help of these two equations 1 and 2, we will be able to write W max divided by Q1 equal to 1 minus T2 by T1, right? And we can write W max equal to, we are taking this Q1 into the right hand side and multiplying it with 1 minus T2 by T1. So W max equal to Q1 into 1 minus T2 by T1. So that will be our maximum work, and that is our available energy. That is our available energy, and we can write it like this: Q1 into 1 minus T0 by T1. T0 is nothing but the surrounding temperature. Here we have taken T2, we have to T2. So here I have replaced T2 by T0 because T0 is the least temperature or the minimum temperature which we can, on which we can reject heat. So this will be our surrounding temperature. So for a given source temperature T1, so here we can see for a given source temperature T1 and for a given input Q1, work is maximum when T2 is minimum. And how we can make this T2 minimum? This T2 minimum is the lowest possible temperature of heat rejection, and that is surrounding. The lowest possible temperature of heat rejection is what? Is our surrounding. So T2 will be equal to T0. Now dear students, we have got the expression for available energy, and the expression of available energy is Q1 into 1 minus T0 by T1. Now we will move to find out the loss of available energy when heat is transferred through a finite temperature difference. So we can see here in this TS plane, this 1, 2, 3, 4, these are the 4 processes which completes a cycle, and this is a isothermal process 2 to 3. We have denoted this by T1, and this 4 to 1 is a isothermal process, heat rejection process. We have denoted it as T0, and the difference between these isothermal processes 0.3 to 2 and 0.4 to 1 is delta S. So Q1 is the heat supplies and Q2 is the heat rejected, right? So if we want to find out the available energy here we can see Q1 is the heat supplied. We are just focusing on the heat supplied. So available energy is equal to Q1 into 1 minus T0 by T1. T0 is the surrounding temperature and T1 is our higher source temperature. So available energy will become Q1 minus Q1 by T1 dot T0. And dear students, we can write this Q1 by T1 as delta S. Why? This, look, if we want to find out the reversible heat transfer Q1, then this is the temperature T1 and this is the change in entropy delta S. So Q1 can be written as T1 delta S, and from here we can write delta S as Q1 by T1. Right? So here we have written Q1 by T1 as delta S. So available energy equal to Q1 minus T0 delta S. So this T0 delta S is our unavailable energy. So we can write here Q1 equal to available energy plus T0 delta S. This is our heat rejected, right? So Q1 is equal to available energy plus unavailable energy. And what is this unavailable energy? We can see it from here, this Q2 heat rejected, right? So Q2 delta S. So Q2 delta S is our heat rejected, right? Q2 is our heat rejected. So here we can see Q2 equal to T0 delta S, right? So T0 delta S. So we have got this expression here, T0 delta S. So this is our unavailable energy, and that is heat rejected. So the minimum heat rejection This is our minimum heat rejection. So this is minimum heat rejection is known as unavailable energy. What is availability? As we have discussed earlier about available energy, it is the maximum work that can be obtained in a cycle. Similarly, availability, it is the maximum work that can be obtained in a process in which the system comes to equilibrium with surrounding. Now, after studying available energy, we will be able to understand that what is the value of temperature, higher temperature and lower temperature. Right, when we are getting here lower temperature heat rejected, then that expression will become unavailable energy. When we are taking the higher temperature and when we will multiply that by our entropy, then that will become our reversible heat transfer, and that becomes available energy. So there is a difference in the value understanding of temperature. Higher temperature is having more value here if we will compare to lower temperature. So according to first law of thermodynamics, thermal energy at higher temperature has same meaning with respect to the equal amount of thermal energy at lower temperature, and hence first law is known as quantitative law. So in first law of thermodynamics, there was no comparison that what is higher temperature, what is lower temperature, right? The thermal energy at higher temperature and thermal energy at lower temperature has the same value. But here, according to second law of thermodynamics, thermal energy at higher temperature has greater significance when compared to same amount of thermal energy at lower temperature, and hence second law is known as qualitative law. That's why we are calling second law as qualitative law and first law as quantitative law. Expression for maximum work in a closed system is W max equal to U1 minus U2 minus T0 S1 minus S2. U1 is internal energy at 1, U2 is internal energy at 2, T0 into S1 minus S2. So this is the expression of maximum work. Now dear students, we will move to irreversibility and Guillaume-Stodola theorem. So Guillaume-Stodola was a scientist and he has given some expressions and he has given a theorem. So what he has said, let's see. The actual work done by a system is always less than the idealized reversible work, and the difference between the two is called the irreversibility of the process. That means that cannot be changed. So that's why it is called irreversibility of the process. This is also known as degradation or dissipation. Irreversibility is also known as degradation or dissipation. That means which got waste. So we can write the expression for irreversibility I equal to maximum work minus minimum work, right? So difference of maximum work minus minimum work. So maximum work will be always our idealized reversible work, and minimum work we may take as actual work. So I can also be written as T0 into delta S system plus delta S surrounding, right? So delta S surrounding and delta S system consist together delta S universe, right? So irreversibility can also be written as T0 delta S universe, and that expression is given by Guillaume-Stodola, right? As we have already discussed, dear students, the entropy of universe can increase, can be equal to 0 but cannot decrease, because universe is an isolated system, right? So as delta S universe is never negative, therefore irreversibility is never negative. So irreversibility can never be negative, right? So we have here two functions. We have taken Gibbs function G equal to H minus Ts and Helmholtz function F equal to U minus Ts. We have written these two expressions by the numerical point of view. In some numericals we can use these Gibbs functions and Helmholtz functions. So that's all for today's class, dear students, and here we have completed our unit number 1. So from the next lecture we will start our unit number 2, pure substances. So that's all for today. Thank you.